One of the final examples that we're going to look at with respect to double integrals is the idea of the application to probability. And in fact, there's a lot of applications to probability for double integrals. For students that have to go through and take a calculus-based statistics course, eventually you're going to run into this thing called a probability density function. And a probability density function is essentially going to be all of the possible probabilities for a random variable x. And sometimes it creates some sort of curve. There's a lot of different curves that utilize models of real-life applications. Many of you have probably seen the normal distribution, and that's one of the curves that we could look at. An exponential sort of regression, or an exponential curve, is another type. Logistic could be used to model something like learning curves, or maybe even animal behavior, etc. And then for random events in which everything has an equal likelihood of occurring, there's a uniform distribution. So for instance, if you were to roll a 6-sided die, the distribution of the probabilities would be 1/6 for each of those. The total probability, or the total area under a density curve, is always 100%, or 1. And we're going to utilize that to be able to help us when we're going through to solve some of the problems to where we have to solve for an unknown constant. So, in the types of problems you'll be faced with, you'll be given the density function, and then you'll just have to develop a double integral to be able to find the joint probability. And when we talk about a joint density function has two random variables, x and y, and we just take that multivariate function and we find the, if you would, the density function of that, or we find the double integral of that. So a very common problem that I recall you finding in statistics was that you're given a density function with an unknown constant c. And what you want to do is solve for c, and then you would want to find p of x less than 1, p of y less than 1. Alright, so here's how the way we're going to solve this. The good news is that we have a rectangular region, and rectangular regions are good because we don't have to find another formula. Alright, so here's how we're going to set up our double integral. Double integral is going to be first the integral. Let's just do dx dy, though it doesn't matter too much. So 0 to 1, 0 to 2. All right, and again, that's just given to us by the bounds. The density function is cx and then 1 plus y. And since we took care of x first, that's going to be dx dy. The total area underneath of a density function, or the total probability, is going to be 1. Alright, so that's our total probability. So now we're going to evaluate the integral. If we do that, we're going to get the integral. We can factor the c out, and let's just integrate the x. So that's going to go from 0 to 2. Antiderivative of x is going to be x squared over 2. We still have the 1 plus y. And we have x is going to go from 0 to 1. And then we still have dy. And that's still going to be equal to 1. Right. After we substitute 1 and substitute 0, it's just going to wind up being 1 squared over 2. So we're going to get c integral 0 to 2 of 1 squared over 2 minus 0 squared over 2, just by our fundamental theorem of calculus. We have 1 plus y dy, and that's going to be equal to 1. When we compute, that just becomes a half. So this whole thing is just a half, and we're going to factor the 1/2 out. So we end up with c over 2 integral 0 to 2 of 1 plus y dy. And that's supposedly equal to 1. We're going to integrate term by term. So that's going to be c over 2. Antiderivative of 1 is y. Antiderivative of y is y squared over 2. That's going to range from 0 to 2, and that's going to be equal to 1. We're going to substitute 2, we're going to substitute 0, so now we have c over 2. When we substitute 2 back in, we get 2 plus 2 squared over 2. When we substitute 0 back in, that just becomes 0, and that equals 1. So what that means is that we're going to end up with 2c equals 1. Okay, so notice that this whole mess right here is just going to become 4. 4 times 2 is 2c, or 4 times c over 2. So we're going to get 2c is equal to 1. So ultimately, that yields that c is going to be 1/2. All right, so that's the first part of this problem. So we go back up and see what the problem's asking us. The problem's asking us to be able to solve for c first, which we just did. Next, we're going to find the probability that x is less than 1 and y is less than 1. So we're just going to have to rework the problem, all right? Except this time we're going to substitute 0 and 1 and 0 and 1 for our bounds instead of 0, 1, 0, 2. And we're going to also substitute 1/2 for c. So now the probability that x is less than or equal to 1 and y is less than or equal to 1 is going to be given by the double integral 0 to 1, 0 to 1. C is 1/2, and then remember our density function x, 1 plus y, and then it doesn't matter dx dy or dy dx because they both range from 0 to 1. I think initially we had dx dy. So let's just keep it in that order. We're going to integrate. So now we have integral 0 to 1 of 1/2 times 1/2 x squared, 1 plus y. X is going to range from 0 to 1, and we have dy. When we substitute 1 back in, we get 1 squared. When we substitute 0 back in, it's 0. So we have a half times 1 minus 0. That's just going to be a quarter. I'm going to factor the quarter out. So we have 1/4 integral 0 to 1 of 1 plus y dy. That's going to end up being 1/4. We integrate term by term, y plus y squared over 2 from 0 to 1. We substitute 1, we substitute 0 back in. When we substitute 0 back in, it doesn't do anything for us. So we're going to end up with 1/4 of 1 plus a half, and I'm going to verify 3/8 in a moment, but I think that's what we end up with. So we have 3/2 times 1/4, and that should give us 3/8, which it does. Okay, so that's the probability. Whenever you get your answer, it should be less than 1, because remember, probability is a value between 0 and 1. All right. So hopefully the integration's not too bad for this one. It's more the concept of how to utilize a double integral to be able to find an unknown constant of a density function and then to be able to evaluate the density of probability given that unknown.